One of the important aspects of organic chemistry is the synthesis of specific targeted organic molecules. And so one of the key skills we need to master is knowing what materials we can use as reactants to create targeted products. Since the Diels Alder reaction is a really valuable reaction for yielding new carbon-carbon bonds and rings, it's important to be able to predict what reactants we would need in order to create targeted products. And that's what we are going to do here. So we'll start with an example problem where we will be given a particular targeted molecule and ask what diene could we react with a dienophile in order to give that particular product. So we have our example problem here where we're asked to fill in a diene that we can react with a dienophile to give this indicated product. Now, in thinking about how to accomplish this or other types of synthesis problems, in general, what I recommend doing is going from generic to specific, meaning thinking first about what is the generic layout of a reaction that reacts a diene and a dienophile to yield a product analogous to this, but a more generic version of it. So when we're thinking about synthesis, going from general, such as recognizing that a diene of some sort reacts with a dienophile, that being a alkene with R groups, R and R prime, to give us our product, which corresponds to creating a new carbon-carbon bond here and here, as shown in this 1,4 cycloaddition by my electron pushing arrows, to create a 6-membered ring by making 2 new carbon-carbon bonds in red and illustrating where the dienophile originated from, like so, with R prime and R there. And I'll highlight, to be even more explicit here, what portion of the molecule originated from the dienophile in blue, and in yellow I'm going to highlight what originated from the diene. And then we take this general scenario and we try to apply it toward the specific product that we've created up here, where we can make comparisons between this specific product and the generic product, where the generic product should have a double bond right there that I initially left out, so I've added that in, has that same 6-membered ring. And for the R groups, that's what we've varied here. The R groups in this specific example are NO2 and an ethyl group. So we need NO2 and an ethyl group here as our R prime and R in our starting material. And that will enable us to create this as our final structure, going from this general example where we plugged in R groups as fillers to our specific example here. So our diene, to accomplish this, just needs to be a 4-carbon diene, like so. And then our dienophile, we'll have our alkene with an NO2 group as one of the R groups and an ethyl group as the other, like so. And if we show our electron pushing arrows connecting the pi bond to the carbon with the electron withdrawing nitro group, then the pi bond on the dienophile comes in and attacks at the other end of the diene group, sending the pi bond over to here to make the double bond in the final product. We realize that indeed, checking our work, that the diene and dienophile combination we've shown here would yield the intended product. Now keep in mind, in this initial example, I haven't shown any stereochemistry of our product here, so I haven't shown whether these two groups are cis or trans relative to one another, and so we don't really need to worry about that here. But there are scenarios where if these two groups were shown as trans to one another, you would need to make sure to use a trans dienophile like we've done here. On the other hand, if the two groups were cis, you would need to start with a cis dienophile instead. Now we jump into another example that is a bit more challenging. So we've got it laid out up top here that we're going to react a diene with a dienophile to yield this as our major product of the reaction with an alkene group right here in the final product. I've also laid out, as before, our general reaction where generically we're taking a diene and a dienophile to give our final product of this reaction. So comparing the generic situation to the specific one up top, it always throws people a bit of a curveball when we have systems that have multiple rings. And that's what we have going on here. So if we look at the structure, we have a ring here that is a heterocycle with that oxygen atom as a heterocyclic atom in the ring, making a 5-membered ring right there that I've highlighted in red. We additionally have within the structure a 6-membered ring connected through like so, with R groups bonded to it as 2 nitrile groups. Now, comparing the structure of the generic Diels Alder product to the specific one up here, we see a shared 6-membered ring with an alkene group in it. So 6-membered ring with the alkene group in it. And we have to relate that back to what our starting structures would be here. So relating back to our starting structures, in our generic example, our alkene had the 2 R groups bonded to it, and the R groups became the branches off of the ring. And specifically, they were the branches that relative to this alkene group were directly across here and here. So alkene group and then directly across here and here are R and R prime. So the same is going to hold true up top here. And I'm going to highlight in gray the portion of the molecule that would originate from the alkene, from the dienophile, based on this logic. So based on this logic of down here, our generic situation, the 2 carbons of the alkene and the 2 R groups corresponded back to the R group here and the R group here and the alkene of the reactant. That's what's shown in gray up top there. So I'm going to scribble that in as the structure of my dienophile, that my dienophile has an alkene, will always have alkene group there, and then it has the 2 nitrile groups directly bonded to it. Now the new carbon-carbon bond that we're making is going to connect from each of the 2 carbons of the dienophile alkene, so that'd be here and here in the product, over to the next carbon atom, which was a carbon that originated from the diene. So I'm drawing those in bold red here just for emphasis. And those would correspond to the red bond here and the red bond here. And so what this is telling me is that position 1, 2, 3, 4 of our diene needs to correspond to these positions 1 through 4 that we have shown here. And then there needs to be an oxygen bridge linking position 1 to position 4. So I'm going to draw that out in red here, that we have an oxygen atom as part of a 5-membered ring, and our diene spans here, over through here, and this represents positions 1, 2, 3, and 4. And looking at the mechanism for this reaction, what happens is the pi bond between positions 1 and 2 comes over, attacks the electron-deficient carbon of the alkene. The pi bond from the alkene comes over, attacks at the 4 position of the diene, and then that bond between 3 and 4 comes over here, like so, resulting in the pi bond that we see in our final product there in blue. So as a result, we make the desired connection between position 1 and our dienophile. That's position 1 over here on the product side and the dienophile. We make a connection between position 4 of our reactant and the dienophile as well. That's shown here as position 4 coming over to the dienophile there. So we've double checked by writing out the mechanism here that we did this correctly. So the bottom line here is, don't let the fact that we have a bicyclic system here in the product throw you off or throw you for too much of a curveball. The thought process for deciphering the reactants necessary here is the same as for the simpler systems. It's a matter of being organized about who is becoming bonded to whom, and remembering that the diene is always going to become linked to the dienophile at positions 1 and 4 of the diene. And if you end up with a system that has 2 rings in it, that means that one of your 2 structures that you started with has to have a ring in it as well, since the Diels Alder reaction always creates 2 new carbon-carbon bonds, that's what we showed in bold here, and 1 new 6-membered ring, and that's what we show in what I'm circling with the laser pointer here as our 6-membered ring. So based on these 2 examples and additional example problems that you can obtain by working through the Chapter 15 worksheets, you should be comfortable in being given a product of a Diels Alder reaction and providing what the expected structure of the diene and the dienophile are that will yield that targeted product.